right, recording is rolling. So welcome back from spring break. Hope you guys had a great break. I know I did. Got a lot of good school stuff done. So here we are on Monday. I'm gonna go over with you guys energy and energy conservation. Okay, so that's what we're doing this week. We're going to be recapping at energy and energy conservation. Remember, that's Unit 5 by AP's book. Next week, we'll do momentum and collisions. Okay. You should have gotten this page. I just handed this out. Did anybody not get this page? It says AP review quiz for Unit 4, Unit 5. Oh, okay. Okay. All right. All right. So I think everybody's got one now. Right? Okay. Let's do this. Let's have these due dates. You guys got your agendas out? Write down some due dates. Got 3 due dates for this class. A few days from now, this Thursday, I want to cover in class AP Classroom Unit 4, Multiple Choice, Part B. So have this done by then, so that on Thursday we can go over those. Okay. And then the week after that, the following Thursday, I want to do for Unit 5, which is momentum and collisions. Right. So have this done by then. Okay. Now these have been open for a few weeks, but yeah, knock them out next couple of days. Well, this next one, for sure. Okay. And then this review page, review quiz page that I just gave you guys. Right, so it's got some energy questions and some collision questions. Okay, let's have that due Monday, April 4. So there's plenty of time to do that. Okay, you guys got this? Okay. Righto. Give you guys some more context. Planned out pretty well most of the rest of the semester here. After we covered those, I want to go back and fill in some other topics that you guys would normally get. So thermodynamics, materials, some engineering type stuff, electricity and circuits. I know I keep promising it, guys, but just rearrange the schedule. So we'll do electricity and circuits. So you guys will learn DC circuits before you get out here. Then go back and review Unit 6 and 7 with you guys. Remember that simple harmonic motion and rotational dynamics. Then we'll do at least 1, maybe 2 full practice exams with the multiple choice. And yeah, that'll take us to May 12th, which is exam day. All right, so energy and energy conservation review. Okay, let's look at that. So energy and energy conservation. You know what? Hang on. Okay, so one of the things that I taught you guys early on in the section was work. Okay. Work has a formula. Guys, what is work? What times what? Force times distance. Yeah, force times distance. Right? Now, this is specifically called a dot product. Okay. Because you can also write this as force times distance times what? Times the, yeah. Huh? Okay, yes, something to do with an angle between them, right? Right. Now it might be sine or cosine, actually, depending on which angle you're referring to. I'll draw a picture for you guys, and then you guys tell me whether it's going to be sine or cosine based on the picture I draw. Right? So I got, say, a block, let's see, some mass, something, it's on the floor. And maybe I've attached a rope to it, and I'm pulling with some tension force sub T, like a tension force, right? And I'm saying this block is going to therefore move to the right. Let's say it's not enough force to pull the block off the ground. I mean, I could pull with enough force for it to like pull off the ground, but let's say I haven't done that. Right? I'm just pulling, so it's just moving strictly to the right, right? And move some distance d. Right now, if I do this tension force times this distance, is that the amount of work that I put into the block to make it move? No, not exactly, because the vertical component of the force doesn't actually do anything. Or it doesn't. Sorry, that's not. straight into it, right? It doesn't move the block, right? Only the horizontal component of the force actually moves the block. So if I dash this tension force into vectors, components, vector components, right? Isn't it just this side part that actually does the work on the block? Right? Now, if I define this angle as the angle between these two original vectors, this force and this distance, right? There's the angle between them. Okay. Now that angle, should I do sine or cosine theta right here?
Yeah, cosine.
This is cosine theta. Yeah. So F times D times cosine theta, that's the same thing as F dot D. If you ever say force times distance, work is force times distance. Well, it's implied that you only care about the parallel components. So this right here, here's another way to look at this. This right here is tension force times cosine of the angle between them. This tension force times this cosine angle times this distance. That's the work that you did. Okay, so that's work, right? Okay. Then what if you take this thing and just turn it 90 degrees so you start lifting the block straight up, right? Well, how much work would it take to lift something? Well, wouldn't you have to apply a force that's at least equal to the weight of that block, right, to lift it? Right? In fact, if you're pulling up at constant speed, you would be applying a force that's equal to the weight of the block, right? And then the distance that you lift it, isn't that like the height that you're lifting it? Right? And if you set the thing on the shelf, so you've done some work to lift it, which means you've given it what kind of energy? Potential energy, and that's the next one I'm gonna do right here. Potential energy. What character are we using for potential energy? Capital U. Yeah. Or I used to do PE. Some textbooks still do PE, but AP likes capital U. Actually, I kind of like capital U too. Right? Sometimes you see a subscript G. Right? And what's the formula for that? MGH. Hey, this exactly aligns with that story I just told you guys. Because mg, that's like the force that you would need to lift that block. And then h, height, is that's the distance that you lift it. So the work that you put into something is the potential energy that you end up giving it. So if I got like some object sitting at the edge of a tabletop, right, has some mass and a gravity field, that means it has some weight, mg, and some height above, say, some floor that's defined as height 0, it has that much potential energy. Ooh, okay. But let me do a side thought here that I did not teach in this order back in the day when I was teaching this stuff. See that G, 9.8 meters per second squared? Right? If you blast a rocket off into space, that actually changes, doesn't it? I mean, if you see this as constant or approximately constant, you can just use MGH. But there is a more universal form of potential energy. Does anybody remember what that more universal form is? It's weird because it's negative. You guys remember this? Negative GMM on R, right? Like I remember GMM over R squared was a gravity force, and negative GMM on R was like a potential energy. And if you have a small radial change, let's say going from like 6,000,001 meters to 6,000,002 meters, where the R value is very small, the R change, I should say, the change in R is very small. You can show that the difference between those two potential energies just boils down to this, like MGH. Right? AP probably won't ask you a question on this. Maybe they won't. I don't know. Maybe for completion, it's just good to kind of know that's there anyway. Okay, so there's a couple different kinds of energy there. Then energy of motion. Right? If I set this on the tabletop edge and give it a tiny bump, it goes here and crashes to the floor. What crashes to the floor with a lot of energy? How much energy? MGH, but it's not that form anymore. It's what form? Energy of motion is 1/2 mv squared. Yeah, right. You're 1/2 mv squared. So that's kinetic energy, energy of motion. Okay. Suppose something's moving twice as fast. Twice as fast has how many times the kinetic energy? 4 times. What if it's 3 times as fast? 9 times. Ooh, right. How about? So I do. Ooh, how about energy stored? Let's do energy stored in a spring. Energy stored in a spring, which is also a form of potential energy. So I'll go back to U, but I'll do subscript S, right? So energy stored in a spring, right? Anybody remember the formula for that?
1/2 kx squared.
It is 1/2 kx squared. Yeah. Right. Where what do these characters refer to? What is lowercase k in this context? Spring constant. How stiff is a spring? And x refers to what? Yeah, how much the spring is either compressed or stretched from its equilibrium position, right? This is for an ideal spring. Let me bring in a graph for this one. Gonna draw you guys a picture, draw a graph. Right? Say you got some spring, and here, oh, hey, look at the spring. It's just hanging out. There's no force on it. It's just doing its thing. It has some stiffness, K. What's the units for K? Newton per meter, right? Yeah. Right. And then I'm gonna put a force on it. Now I need an equal and opposite force on both sides. Compress some force F. That's gonna compress it some amount X, right? Okay. So put a force or squash the spring, changes by some amount of X, right? Now, if this is an ideal spring and it follows Hooke's law, what does an F versus X graph look like? Can you guys draw that? Did you guys just draw that right there? Right? F equals KX. That's Hooke's law, isn't it? Some textbooks say negative, depending on how you're reading the force, but F equals KX. I'm getting ahead of myself. Right? Now F equals KX. I don't see anything about energy in F, right? Because this is from unit 2. This is review from back before spring break, right? Now, how does this tie into energy stored in the spring? What property of this graph is the same thing as energy stored in the spring? Well, let's go over different properties of this graph. What is the slope of this graph? K. That's the stiffness of the spring, right? Okay, so the slope is the spring constant. Any particular coordinate is the amount of force that you're putting on to smash it some amount, right? Like if you want to smash it this amount, you have to put this much force on it. That's that point right there, right? What property of this graph represents how much energy stored in the spring? Area under the curve. And if it's Hooke's law, F equals KX, I feel like the area of a triangle, right? Okay. So maybe I'll call some generic value X and some generic value F, which is equal to KX, right? If this base is X, say that, right? Okay. Isn't the area of that triangle, therefore the energy stored in the spring, equal to 1/2 base height of that triangle? So it's 1/2 base height. Now height is F, but I'll just call that KX, right? Because F is KX, right? Oh, look at that. 1/2 KX squared, which is what you guys told me. So that's 1/2 KX squared, energy stored in the spring. Right? Listen to that. Right? In fact, you know what? That graph, that set of axes, F versus X, you are going to get probably more than one graph on the AP exam where you see F versus X. And I'm already predicting not only that you'll see more than one graph with those sets of axes, but what the question is going to refer to. The question is probably going to refer to something to do with like how much work was done on or by the system, or how much energy is stored in the system. Right? So something to do with work or energy. Right? And the answer is always the area under the curve. So for example, okay, there's a real good chance that on May 12th, you guys are going to get a graph. Okay, you'll see these axes, something to do with a force measured in newtons as a function of some displacement measured in meters. Right? You might see a scatter plot. AP likes these type graphs too, right? It's like 2 students do this experiment and they get this data. All right, and it's, I don't know, or they're pulling a block with a force probe, and it's a constant force. That is a constant force, isn't it? It goes up and down a little bit. It's pretty constant across. Right? So how much work did they do on the block? Maybe it's some setup like this. They got a block. They got like a spring scale force probe, right? And they're pulling this thing with some force for some distance, right? Fx. They're pulling that block, right? And how are you going to solve for how much work they did on that block? F times X, right? Say, well, this is approximately constant. They did it for this distance. I got a nice looking rectangle right here. Right? Do this force times this distance. Boom. That's how much work was done moving that block. This force for this distance, right? You can do that. I bet you guys are going to see that. See, for okay, a couple more things, and then we'll start to set up some conservation of energy equations. There's also, okay, there's one more building block I want to cover, because what have we covered so far? Did work as force times distance, well, the dot product between these two. Potential energy, gravitational is MGH. You might see this one, but probably not. So MGH, definitely know You guys know energy stored in a spring, 1/2 kx squared. Here's the graph that backs that up. You guys know energy in motion, 1/2 mv squared for kinetic energy. No, that's for like tangential motion or motion in a straight line. You could say something like that, right? But the last building block I want to cover here is what about something that's rotating? Like if I have a rotating turntable, right? Ooh, it took some force times distance to get that to move, right? So I'm forced for some distance. So I just put some energy into this turntable, did some work on it to get it to spin. Okay? And then, ooh, this feels pretty hefty. It's got some width to it. It's got some mass, right? So I got this mass that's rotating, but if I break this into a billion points, every single point is moving at a different speed, has a different V, right? Well, unless it's at the same radial size, but right. So how do I add up all the 1/2 mv squared of all this crazy disk? Well, there's a more efficient way to think about it, and that's to say kinetic energy rotational is equal to, and what's the formula for rotational kinetic energy? 1/2. Instead of m, what's the stand-in for m in rotation? I. Instead of v, we're doing omega. Yeah, 1/2 I omega squared, right? You guys remember I is the sum of mr squared? Like for a single point, it is mr squared. For a solid cylindrical disk spinning like this, it's like 1/2 mr squared, right? Omega, that's how fast something's spinning, like angular velocity. Right, so like radians per second. Okay. By the way, omega is the same thing as v over r. Right, ever came to that? Okay. Okay, so I'm done with the building blocks. Let's recap this idea of a closed system versus an open system. Because if a system is closed, what does that mean? And there's two perspectives that I'll take on that. If a system is closed, then what? Yeah, okay, yeah. Energy is conserved. So there's, what's that?
It's conserved in the system.
True, yeah. So there's, yeah, so energy is conserved. And that,
No outside forces.
yeah, no outside force, no external force. Right? And one sort of implies the other, because let's say you have like some system that's roped off, right? Let's say this is my system. I don't know if there's like, maybe there's like carts colliding or, well, collision's more like a momentum thought. Anyway, maybe pendulum swinging. Hey, maybe pendulum clocks go boom, like Newton's cradle. I don't know. So, okay, but that's my system, right? Okay. Inside this bubble, inside this system, okay, you could set up a conservation of energy. That's where I'm going with the story, right? So that there's no energy that leaves or enters that system, right? And going hand in hand with that, there's no external force on or by that system. So there's no outside force pushing on the system. That system's not pushing on anything else, right? Right. So yeah. Well, work is force times distance. So, I mean, if you had an external force for some distance, that would imply some kind of work done on the system anyway, right? And so that's gonna, especially this point, this top point, it's gonna lead to this right here. Sum of energy initial equals sum of energy final in that system. And then, okay, so this is if the system is closed. Now, if it's open, you can do like initial energy plus or minus some work is equal to the final energy, right? It's a little trickier, but right? But if it's a closed system, then it's just this. And you can use this as a framework to solve all sorts of problems. Set up some of these problems. Start off with a real basic one, and then we'll get some more fun type ones. All right. So classic example that I use over and over is Leaning Tower of Pisa. Let's give this some architectural patterns. Galileo runs to the top of the Leaning Tower, reaches off, drops a bunch of stuff. And what do we got here? These things have different masses, maybe. There's some height above the ground. I'll call it H. Okay. Maybe I'll define the ground as being height 0. Because remember, with these conservation of energy steps, you want to establish some height 0 somewhere. Okay, if you want to use MGH, right? So there's some height change. Right? And maybe what I want to know is when these objects are about to hit the ground, point A to point B, initial to final, right? How fast are they moving? What is the V, velocity? How fast are they moving, right? Now, you could actually solve this particular problem back in unit 1. You guys remember something that looks like this? V final squared equals V naught squared plus 2AX, right? That was it's the third of these 3 kinematic formulas. You guys remember those? Right, this guy right here. This is the one that does not mention time, even though time's passing, but right. So you guys have had a way to solve that for a long time in this class, but there's another framework that you can use, and that's this conservation of energy. Sum of energy at the top of the tower equals sum of energy at the bottom of the tower. Right? Oh, by the way, what objects are actually involved in the system? So I can set this up so I can solve for what is the V speed of each object about to hit the ground. Okay. Is it just the object? Is that what's the only thing in the system? And the Earth. Yeah, you're right. Right. So I might call this like the object Earth system, right? The object Earth system. You have to include both those things because Earth is providing a gravitational force on each object. So what type of energy at the top? Potential energy, MGH. What type of energy right above ground level? Kinetic, 1/2 mv squared. Right? This might be initial, this would be final, right? And that's it, because if Galileo drops them, doesn't throw them, then there's no kinetic to begin with. And the objects are hitting height 0 at the end, that means there's no potential energy at the end, right? So it's just, this is equal to this. Remember the point of the Galileo experiment was to show that the mass didn't matter? Well, there it cancels out right there, right? And you can solve for this V final. You guys see 2 algebra steps, cross multiply the 2, take the square root 2GH. But you guys have seen this so many times, but by this point in the class, but hopefully you've taken this to heart. Like, okay, if I'm just dropping something, then I know the speed it's picked up to is square root 2GH, right? You guys would know that, right? Because this might be one small piece of a larger, more complex FRQ question. It's like, okay, well, here's one of like 4 or 5 different steps that you have to do. And if you know this, right, okay, well, I know that part of the picture. It's because I set this up, show the AP grader, I know that's how I got this, and then move on to like part 2 of 5 or something, right? Okay. Oh, and you know, just for completion, let's see how that compares back to how you would have done this back in unit 1. You guys remember this kinematic formula again? So if he drops it from rest, that means V naught 0. So 0 squared is still 0. A, that's like G. X, that's like H. Square root. Oh, do you guys see it's gonna be the same thing? Okay, so you guys know that. Okay. Let's do this. Gonna bring in. You guys remember this? Back many months ago. If you want to find this on Google Classroom or in your folder, you have a 3-page energy table. I haven't printed out new ones, except for myself. But I'm going to be referring to this table, and we've done all these before. But let's take a look at some of these again. Let's start with car brakes to a stop. So car brakes to a stop. Okay. Right. See if you guys can set up a conservation of energy equation that could somehow describe something that's going on here. So there's some, let's say, initial velocity of the car. It comes to a stop. This car has some mass m. And let's say the stopping distance is like, let's call it x. Right? Can you guys set up a conservation of energy equation to go from point A to point B, right, initial to final? Something like that. Trying to give you guys a head start here. Okay. Okay. You know what, too? Over on the side, I'm gonna set up a free body diagram just because it's gonna help me make a certain point later on. Okay. So when the car was in motion, well, let's say it's like breaking to a stop. Now, I know I'm going back to a couple of units here, back to unit 2. You guys remember free body diagrams? That's like a unit 2 type thing, right? but maybe this car has a weight mg. Maybe there's a normal force from the road that's exactly equal to mg as long as it's on a level road, right? It's not going up any hills. Okay. And then if this car is braking to a stop, then what's the last force? Okay, friction that opposes the motion. It's like friction force, because okay, that's a side thought. You don't actually need this to set up the conservation of energy, but I'm going to refer to it later anyway. Okay. All right, did you guys set up a conservation of energy equation? Okay. Do you guys say sum of energy initial equals sum of energy final? Okay. To tell you what, there's actually a couple perspectives you could do, set up slightly different setups. If you assumed a closed system, then you'd have to include the car and also the road, because do you guys think if this car is switching to stop, that there's some thermal energy going into, say, like the tires in the road, right? And you would have to account for that. And that's not mechanical energy. We don't have a nice clean equation for that. Well, we say MC delta T, but I'm not really doing that in this class. Right? But you could say something like this. The car had 1/2 mv squared, right? And all that energy went into the work done by friction. And I call that force of friction times distance, right? Maybe there's technically a little bit better way to think of this, and that's as an open system. Let me show you what that would look like. Sum of energy initial minus work done by friction leaves you with final energy. Okay, so this would look like 1/2 mv squared minus force of friction times distance is equal to, and if it's a complete stop here, no elevation change, I'd say 0 joules of energy. Right. So everything below the squiggle line is interpreting it as an open system that just consists of the car. And then above, yeah, you could force this into a closed system if you also accounted for the thermal energy, and it might look something more like that. Right? But hard to think of it. How about this? What if you, we'll say you're driving around roads, right? You screech to stop, it takes you some stopping distance, let's say like 10 meters. Right? And then you go to the grocery store and you load up on groceries. You're just like loading up for the apocalypse, and you double the mass of the car. Right now, your car is full of groceries. It's twice as heavy, and you're going the same speed as before. You're, okay. What's your stopping distance now compared to before? The car is twice as massive. Let me give you guys some options and let's see, show hands. So twice as massive car. Option A, it goes the same braking distance. Option B, it goes twice as far. And option C, it goes 4 times as far. For double the mass of the car. How many guys say the car is going to go the same distance as before to stop? Screech the same distance to stop. Right. Textbook physics. Who says double the distance? Does anybody say 4 times the distance? If you said 4 times, you're probably thinking of something a little different. The correct answer was the same distance. The same distance. Right. Now, if you try this in real life, you might work a little bit, but we're talking about textbook physics, right? Right. Now, why would it? Now, you might look at this and say, well, if I double the mass of the car, wouldn't I be doubling the kinetic energy? Which is true, right? Why would X have to be the same? Because that, now here's where the free body diagram comes in. That's why I do this free body diagram. Because if you double the mass and therefore the weight of the car, doesn't that double the normal force? And friction force, isn't that equal to coefficient of friction times the normal force? Coefficient of friction is just a material constant. So if that doubles, that doubles, that doubles. Okay, so doubling the mass implies a doubling of the friction force. That's where the doubling went. Okay, so it's the same stopping distance. The mass of the car does not affect the stopping distance of the car at all. Okay, if you get that question on an AP, you increase the mass of the car. What happens to stopping distance? The answer is it doesn't change at all. Okay, right? Kids got that? How about this though? What if you take your car full of groceries and you double the speed of the car? So now instead of going 10 miles an hour around the neighborhood, they're going 20 miles an hour. So you double the speed of the car. What does that do to the stopping distance? Does it have no effect, double it, or quadruple it? How many guys say that if you double the speed of the car, it's going to have no effect on the stopping distance? All right, yeah, nobody said that. Who says if you double the speed of the car, it's also going to double the stopping distance? Who says it's going to quadruple the stopping distance? Yeah, you guys got it. Doubling the V quadruples the stopping distance, because doubling the V factor 2 squared, you get 4 times the kinetic energy. And that factor 4 does all route into the stopping distance. Okay. What if you triple the speed of the car? How many times the stopping distance? 9 times. All right, let's move on to new example. Let's have a, where's the table? Let's do another car type example. Let's have a Pinewood Derby car. Pinewood Derby car. Yeah, set this car up here. A little bit. Did I show you guys a Mark Rober video on Pinewood Derby car? No. Yeah, I'm going to jot down his name here if you want to check out his channel. He's a former NASA engineer. We're really good at his channel. Mark Rober. Right. And let's have the finish line down here. Because one of his videos on Pinewood Derby car, he tells you how you can maximize the speed of this car and therefore like win all the races. And the framework they use is conservation of energy. So it's just sum of energy initial. You know what? Here's a. Do you guys know work energy theorem? Right, the work you do on something is the energy it changes by. I'm going to say minus work done by friction is equal to the energy that you end up with. Right, but I'm just going to rearrange this so it looks kind of like a closed system. Right, because I mean, if there's friction acting on the car and you consider the car Earth system, here, how about this? If it's a car Earth system, that would be open system if there's friction between the wheels and the track. Right? If you include the track, then maybe you close it again. So all right, so I'll say this: sum of energy initial is equal to sum of energy final in the system, also including I'll say plus work done by friction. See, I'm just going to add it over, right? Just to think of it like a closed system like that. Okay, so what kind of energy did this car start off with? Potential, gravitational potential energy. Right? This is all MGH. Okay? Now, where did the energy go by the time the car gets, say, like down to here? What's one place it went to? Kinetic energy. It better be in motion. Gonna win some races. 1/2 mv squared. Right? Plus, well, I'll say maybe there was some friction down on. So I'll say work done by friction. Yeah, whatever. I should really subtract that from the left side, but you guys get the idea, right? Right. And then, how about this, guys? If those wheels are spinning and the wheels have significant mass compared to the car, then what type of energy is that? What type of term would take care of that? Spinning wheels. 1/2 I omega squared. Right? Right? Yeah, like rotational. Right? Wouldn't that be true? Right. So here's where the energy comes from, and here's the places that it's going to go to. Right. And in this particular video, he tells you that one of the biggest tips you can do to win Pinewood Derby races is to actually bend one of the axles so that only 3 of the 4 wheels actually touch the track. Okay? Now, why does that help? It helps on a couple of fronts. One is that if you only have 3 wheels spinning, well, that's 25% less energy that's going into like friction between the wheel and the nail, right? Right. But also that's 25% less energy going. Like this term would also be 25% less, right? Because now you have 3 instead of 4 wheels spinning, right? So if you had like 100 joules, say 100 joules. Let's say it was like, like 50 went here and then like 30 went here and 20 went here, something like that, right? Well, if you can reduce these 2 terms, then more energy is going to be routed into the linear kinetic energy, and those cars win the races. Right? The cars that ride on 3 wheels always win these races. Okay. How about let's do this type setup. I got a block smash against a spring. Now, did it take some work to force times distance, smash that block against that spring? Right? Okay, so there's some stored spring potential energy. Then I let go. Pew! Let's say the second point I'm interested in, it's like flying up here. It's got some V velocity. Let's say this is a low friction system. Yeah, I should have made the Pinewood Derby a low friction just to simplify that one too. But all right, so or I should say negligible friction. Let's not say low friction. Let's say negligible. Sounds more scientific. Negligible friction. So basically no friction. Okay. Can you guys set up a conservation of energy for this? First of all, what system are we dealing with? What's in the system? The block. What else? The spring and the earth. Yeah, the block. This would be the block, spring, earth system. Okay. Like if I was going through an AP exam and I saw this picture, I would start reading the text saying, oh, please, I hope in the text it says block, spring, earth system. And if I saw that, I'd say, oh, yes. Okay. Because if it said block, spring system, that would be a what kind of system? Open or closed? It would be open, right? So you have to include the earth for it to be a closed system, right? There's definitely some height change in that block from point A to point B, isn't there? Right? So see if you guys can beat me to the setup. Sum of energy initial equals sum of energy final. Okay. Go ahead and write out the conservation of energy equation for that right there. Give you guys a head start. All right, you guys figured it out? Did you guys say 1/2 kx squared is the source of all the energy? Yeah. Right, it was all stored in the spring. And then by the time it gets up here, where'd that energy go? Yeah, gravitational potential. Oh, I should have labeled the height change here. We gotta do that. There's some height change h. Okay. Yeah, some of the energy went into lifting it lifting it. And then whatever was left over went into kinetic, 1/2 mv squared. Right? Okay, so that turned into that. I think that's it, right? Now, maybe a kind of a lower level question with this would be like, if you were given a certain number of things, like let's say you knew the mass of the block and the stiffness of the spring and how much you compressed it and the height change, could you solve for V? Could you solve for how fast this block was going? You just go plug, just plug everything in and solve it, right? A higher level question that AP would be more likely to ask would be like, well, if you change one variable, all else equal, how does that affect something else? So how about this? What if I take this height change and I increase the height change? Maybe it's like a wireframe and I kind of twist this around and I like double that height change. Can you guys imagine that? If I double that height change, right? All else equal, same block, same spring, same compression. What happens to the speed of the block? Does the speed of the block increase or decrease as the result of this height change increasing? Let me see a show of hands. How many guys think if I increase the height change that the block is going to speed up? How does we say it's going to slow down? Yeah, you guys are right. It is going to slow down. Now, here's the energy accounting way to think about this. Say this is like 100 joules of energy right here. Maybe it went into like 50 joules here and 50 joules here. And then you divide by the mass of the block and times 2 square root, you can find the V, right? But if you increase this H, I said double it, but maybe that's like too much. But let's say you just increase it in general, right? So you might have 100 joules, starting energy maybe goes into like 70 joules of MGH. And now there's only 30 joules left over to go into kinetic energy, right? I mean, this is the same principle of, say if you're going over, say Vera Boulevard over I-95, you know, that like weird interchange they have, right? And you just take your foot off the gas and just let the car like coast up the hill. Isn't it gonna be slowing down as it's going up the hill? Yeah, rolling up the hill, it's gonna be slowing down. Let's do the bungee jumper. Guys ready for a bungee jumper? Actually, the question I'm about to give you guys right now, it's gonna take some thinking, but it's very similar to a past FRQ. So here's what we got. Got a bungee jumper. It's gonna jump off the edge. Gets to about here. And here's this bungee cord. Okay. And then he falls a little bit more, and see right about here, the bungee cord finally goes taut, and then it stretches all the way down to here. And at that point, it's maximally stretched. Okay. I'll label some things. Let's say that this right here is the L length of the unstretched bungee cord. Everything down here, I'll call X. That's the amount that it's stretched beyond its original value, right? And if you put those two together, let's say at the bottom of X, he's really close to hitting the sidewalk down below. It's called the full thing H. And maybe I want to know what's the highest like bridge I could jump off with this bungee cord and like be okay, or something like that. What's in the system? This is a what system? Like a person, earth, cord. Yeah, person, earth, cord, person, cord, earth system. Right. So we're gonna have a closed system, and let's treat the bungee cord as an ideal spring. Can you guys do that? Can you guys treat the bungee cord as an ideal spring? All right, beat me to the answer here. Sum of energy initial equals sum of energy final. Okay. Set up a conservation of energy equation. Conservation of energy. There might be more than one way you could write that on your paper. Give you guys lots of variables measured in meters there. This guy has some mass, right? This guy has some mass M. Yeah, bungee sport cord has some spring constant K. Is that okay? Okay. Right. Oh yeah. Okay, yeah, actually, your question's gonna lead to my next question. Okay, do you guys all write a conservation of energy equation? Because here's the next thing I want you to do with that equation on your paper. You may have written a little bit differently from each other. Can you rewrite what's already on your paper so that you can solve for H? I want to know what's the maximum height bridge I can jump off, okay? And not have X in the equation. Okay. If you wrote X somewhere on your equation, that's fine. You just have to substitute it out. Can you guys do that? Okay. So see if you guys can get 2 steps ahead of me now. So not only do you have just some conservation of energy equation to explain that story, okay, but now you're substituting out X and only having it in terms of H and L, and also as mass and also spring constant. Okay, but no X. Can you guys do that? If you can do that, okay. So I'm thinking, oh, you know what? I do have 4 different pictures, and remember these conservation of energies. I need to pick 2 of those pictures. So we're going from this top picture to this very bottom picture. So initial to final. Okay. Now after this, of course, the bungee cord's gonna boing, pull them back up, and it'll like oscillate for a while. So let's go. MGH, wasn't that his original energy? MGH. Okay. Okay. And then by the time he gets to the bottom, that energy went into where and where? Or maybe it's just one place. They go into 1/2 kx squared. Yep. If he's pretty much at ground level, there's no gravitational potential energy. Well, oh, does he have kinetic energy at the bottom? No, because it's like maximum stretch, right? Now maybe I have kinetic energy at this point or this point, but those points are not in my setup. I care about beginning to end, right? Start, right, point A to point B. Okay. So that's the whole setup right there. Okay. But I said one more thing. I said don't do it. Don't write S, the stretch amount. I want to solve just for H, like maybe like this H right here, right? Right. But this X, yeah, it is also related to that H, right? Like however much you can stretch has something to do with the bridge height. So how did you guys handle that?
H minus L.
Yep. H minus L. Right? Do you guys substitute that in? Okay. Because then you guys see go to the store and just measure the unstretched length of the cord. That's what L would be, right? So it'd probably be pretty easy to get that number. Okay. Okay, all right, so there, you could solve, do you guys see in principle, you could solve for H, right? Ooh, do you guys see that it's gonna be quadratic, right? I mean, if you went through the full thing and solved it out, if I gave you guys some numbers, you would have to probably apply a quadratic equation at some point, right? How about this? If I swap out this guy, let's say this guy's like 40 kilograms, and I swap him out with somebody who's like twice as massive, like 80 kilograms, right? 40 to 80 kilograms. Do you think this is gonna stretch even further than before? Does mass make a difference? I think it's so, because if he has twice the mass, wouldn't he have twice the initial potential energy? Right? And then so the amount of energy that would have to go into the spring, or well, the cord, which we're treating as an ideal spring, right? That would also be doubled. Is that going to be double the stretch length though? Go back a few pages of my notes. Does double the energy mean double the stretch length? So like, we're treating this as this guy's bungee cord, right? Right. So here, let's say it stretches like that amount. Right? And the area of that triangle represents the energy stored in the curve. Okay. So like right, like up to here. Right. If you want to double the amount of energy, say if you double his mass, you're going to double the potential energy, right? Once you go to the right until you double the area of the triangle, and it's only that probably right about there. Probably right there. Right. So the amount that it stretches now, is that twice as much as before? Or is it less than or more than twice as much? It's less than twice as, yeah, less than twice as much. You guys see that? Right? Ooh, that might be a really good AP question right there, right? So I'm like this scenario, if you double the guy's mass, how much does it stretch? And the answers might be something like less than twice as much, same as much, twice as much. I don't know. Right. Right. How about let's do the universal gravitation, because we don't do too many, and you probably won't get this on the AP exam, but it's good to know. I mean, like if you do the one we're about to do, then have a real good handle on this class. Okay. So let's take out a couple of asteroids. I'll make them with the same mass as each other. Okay, so like 1,000 kilograms, 1,000 kilograms, two tiny asteroids, and they're separated by some distance. Well, let's call it x1, I guess. X1. Okay. Let's say it's floating around in space and there's no well, actually, let me change it to not, like x naught, because you go initial to final, right? Okay. Ooh, looks like my frog has a nose ring. And there's no initial velocity, so there's no kinetic energy. Relative, I don't know. Right? But they're under each other's gravitational influence. So they start to pull together, right? There's gravitational force. Right? They start to speed up as they're falling towards each other. That's the before picture. Let's say the after picture looks something kind of like this, where they're just about to crash into each other. I wonder how fast they're moving. How fast they're moving. V, as they're about to crash into each other. Now, is right at the point that they're starting to crash into each other, is the distance between them 0? No, because guys, distance in physics, is distance surface to surface or center to center? Center to center. Yeah. So I'll call this x final, right? You guys see an x initial, x final? Hey, you guys see that? Okay. And if you want to know how fast they're about to crash into each other, then you could set up a conservation of energy. So sum of energy initial equals sum of energy final. This would be for the 2 asteroid system. I mean, that would be the whole system, right? Okay, so the 2, we'll spell that out. 2 asteroid system. Can you guys set up that conservation of energy? This one's a little tricky, but I think you guys can figure it out. Give you guys a head start here. At the beginning, I said there was no kinetic energy, right? At the beginning anyway, right? So there's no kinetic here. I don't see any springs. What kind of energy at the beginning? It is potential, gravitational potential, right? But do you want to write MGH? No, because that little g is definitely going to radically change as they get closer together, isn't it? You want to write what? Yeah, negative G M M on, well, let's say R, but say X naught, right? Right. Ah, right. And then in the final, I bet you guys can finish this now. In the final state, remember, initial, final, what kind of energy there? And yeah, go ahead. Did you guys write negative G M M on X final plus 1/2 mv squared for the left asteroid plus another 1/2 mv squared for the right asteroid? You guys do that? Right. Right. And if they have the same mass, then they'll have the same v. So if you got some numbers, you could eventually solve for v, right? Or even if you didn't have any numbers, you could solve in terms of variables, right? You could do that too. Okay, you guys got that? All right. Well, you know what? We're real close to the bell, and that's about as far as I got with my other class. So we'll call that a wrap on today. Tomorrow, I've got some more fun questions lined up for you guys.